So our next speaker will be Sylwia Ostrowska from Southampton. And I'm very much looking forward to a talk about continuous flow PHIP. Good luck.
Thank you very much. And can you hear me well? Sorry, can you, oh, no.
It was perfect.
Oh, okay. All right. Let me start then. So I would like to first start by thanking the organizers for giving me the ability to present our work at this conference. And yesterday, Marcel gave a really comprehensive and great motivation why we are pursuing micro NMR, and today I just would like to give a little reminder for my work. So lab on a chip devices or just chips are increasingly used in the life sciences to study biochemical reactions at a much smaller scale compared to the conventional reactors. But the main advantage is the fact that we can study the reactions at a really well-controlled environment. And since biochemical reactions occur at very low concentrations, we need to incorporate hypopolarization methods with our devices to boost the signal. And recently our group have presented the integration of para-hydrogen-induced polarization with our devices, and what it yielded was a continuous stream of hypopolarized material with a picomole mass sensitivity. We used 50% para-enriched hydrogen, and we obtained signal enhancement of 1800, and that equated to proton polarization of 8%. Now, to make this approach practical, however, we need to enhance the yield of the reaction, as it was only about 2%. And to do that, we need to understand the interplay of the chemical reactions and the transport properties, as well as spin dynamics in the fluid flowing through our devices. So today I'm going to walk you through firstly our space-independent model, a kinetic model, followed by the space-dependent model, which helped us understand what is actually happening in our chips. So now the reaction that was implemented was the first step of the sidearm hydrogenation, where propyl acetate was hydrogenated in the presence of this rhodium catalyst to yield allyl acetate. And the reaction was done in methanol D4. Now this reaction occurs by the following mechanism. Maybe I'll just switch to the laser pointer. So the first step of the reaction is the catalyst activation, where the inactive catalyst A reacts with hydrogen to form the active catalyst species B. So what happens in this reaction is the cyclooctadiene gets hydrogenated to form a cyclooctene. Now, once we have the active catalyst, propyl acetate can enter the catalytic cycle to form the complex C. And upon further addition of hydrogen, propyl gets hydrogenated to form allyl acetate. However, since this catalyst is not selective, allyl acetate can re-enter the catalytic cycle, and in the same manner it gets hydrogenated to propyl acetate. Now, of course, to create a kinetic model, we need some experimental data to fit it to. So just for convenience, we have created this set of data in a 5mm NMR tube in a high field magnet. And in the tube, we had a precursor solution containing 20 millimolar of propyl acetate and 5 millimolar of rhodium catalyst. Thermal hydrogen was bubbled at 5 bars for 10 seconds, and a transient was acquired every 40 seconds until 72 seconds. Now, from this data, we have obtained the concentration profile for the reactants involved in for the reactants as a function of time. And here I'm just highlighting the areas which were integrated. And in blue, I have highlighted the propyl acetate. In orange is the allyl acetate, and in green is propyl acetate, and then it's red for our catalyst. Now, moving on to our kinetic model, we have assumed a 20 millimolar steady state of hydrogen and a starting concentration of the catalyst, the unactivated catalyst, to be 5 millimolar, and 20 millimolar of propyl acetate. So now this is also all our reactions were irreversible. So this is our starting situation. And now in the first few seconds of the reaction, we are forming the active catalyst species. And once that species is formed, propyl acetate gets rapidly consumed. And the rapid consumption of propyl is reflected in a very fast formation of allyl acetate, which is the first hydrogenation product. Now, lastly, we move on to the last hydrogenation step. Allyl acetate goes to propyl acetate. And now on this figure, the solid line corresponds to the best fit for our reaction rate constants. And these were obtained using a non-linear model fitting. And the table lists these constants right here. Now, so this is our space-independent kinetic model. And now let's move on to our chip reactions. So all the reactions performed on the chip are done in a high field NMR spectrometer. And in the magnet, the chip is placed in a home-built transmission line probe. And the device itself sits between two strip-line planes with the sample chamber aligned right there in the constriction of the strip-line planes. And this is the top view of our chip. And the precursor solution, still containing the same 20 millimolar of propyl acetate and 5 millimolar of catalyst, is delivered using a syringe pump into this blue solution channel. And pure hydrogen is delivered via a separate channel shown in red. Now, for the reaction to occur, hydrogen needs to penetrate through the PDMS membrane and dissolve into the solution. And in here, the PDMS membrane acts just like a bridge between the two channels. Now, most of the reaction happens, of course, here in the hydrogenation region, but as well, the reaction occurs downstream, and we detect right here in the sample chamber. So how did we simulate our devices? So what we have done is we've created a 2D representation of our chip. So now our simulation domain consisted of a reaction pathway here, right, shown in blue, with a sample detection chamber. A second domain was the PDMS membrane. Now, all the dimensions were adjusted such that they reflect the actual volumes present in the chip. And that was so the reaction pathway together with the sample chamber is approximately 8 microliters. And so now the flow pattern in the reaction pathway was found by solving Navier-Stokes equation, and the resulting velocity distribution was used in the diffusion reaction convection simulation of the hydrogenation reaction. And the gas channel wasn't modeled explicitly, but what we have done is imposed a constant concentration at the appropriate boundaries. So what I actually mean is that constant concentration of hydrogen was imposed firstly on this outer boundary of PDMS membrane, and it's just labeled as HPDMS. And now the membrane was coupled to the reaction pathway via a second boundary right here, which is a concentration of hydrogen in the reaction pathway is equal to the concentration in the PDMS membrane. And now, firstly, to test our model, we have looked into the hydrogen uptake of the chip. So the concentration was set at this boundary to be constant, and it was 20 millimolar. And this boundary remained the same. And now all the reaction constants were set to 0 in the flowing liquid. So we still solve for the flow, of course. And so on this graph, what I'm showing is the hydrogen concentration only in the sample chamber as a function of flow rate. And the open circles are, correspond to the NMR measurements, and our solid line corresponds to our simulation. So as you can see, at low flow rates, our simulation predicts the concentration of hydrogen quite well. But once we get to higher flow rate, the simulation doesn't reflect it well anymore. You can see that the experimental data just drop off much more rapidly, whereas simulation is steep and still smooth. This can be further understood looking at the hydrogen concentration distribution over the entire length of the chip. The green area here, the green shading, shows the PDMS membrane as well, and the white is the remaining part of the chip. Now, at very low flow rates, so 0.5 microliters per minute, the hydrogen concentration builds up really steeply and reaches a maximum. So the channel gets it gets saturated, and then it remains constant. But once we move to higher flow rates, such that 3.5 microliters, we actually are unable to saturate the channel to the full extent. So we're saturating it only to 10 millimolar, and then as we go further down in the flow rate, we reach only approximately 2.5 millimolar concentration of hydrogen. And we were quite happy with these simulations, so we moved on into the full simulation. So now we still have the constant concentration at this boundary, but what we do now, we also include all of the reaction equations. So just one additional note. On the chip, we're actually interested in the concentration of the hyperpolarized allyl acetate. But whereas in our previous kinetic, space-independent kinetic model, we have haven't included any relaxation of the product. So here we're simply including a reaction where hyperpolarized allyl acetate goes into the just relaxed allyl acetate. So Al goes to La2 with the rate constant of 0.14 per second. And here we're still looking at the concentration at the sample chamber. So this is the distribution of the hypopolarized allyl acetate concentration at different flow rates. So at 0.5 microliter per minute, there is no concentration in the sample chamber. And now as we move to higher flow rates, we get approximately half a millimolar, and then moving on, we also lose, we begin to lose the products again. And this can be better visualized just by plotting it, by plotting the hypopolarized concentration still as a function of flow rate. And yesterday in his talk, Marcel mentioned that this curve, this very steep increase optimum and then very steep decrease puzzled us. So now with our simulation, we can understand that at the beginning, this very steep rise is due to the fact that the allyl acetate is formed upstream somewhere in this channel upstream from the sample chamber, and is then carried just passively into the sample chamber until, of course, as we increase the flow rate, there is an optimum where most of the product is being formed in the sample detection chamber. And after the optimum, so when we reach higher flow rates, we are just simply not picking enough hydrogen to then actually form the product. So we are quite happy with our simulations, and I will conclude here. So we have developed a space-dependent kinetic model for a PHIP reaction using independently acquired data with no adjustable parameters. The model predicts well the hydrogen uptake and the concentration of the allyl acetate in the chip. And these simulations will be used to aid design of more effective microfluidic reactors. And lastly, I would like to acknowledge everyone that helped me throughout and worked on this project. Firstly, with my supervisor, Marcel Oets, my co-supervisor, Giuseppe Pilao, and our collaborator, Malcolm Levitt. And I would like to also acknowledge Billy, William Hale, and Manvendra Sharma, and James Eels, which pioneered, or which did the previous work on the chip. And also Christian for helping me with Mathematica simulations. And thank you all for your attention.
Thank you so much, Sylwia, for this very exciting talk. There are a couple of questions. First of all, a very simple one, I hope. So have you considered the flow profile itself? I assume the flow is laminar.
Yes, it's a laminar flow because we are very low Reynolds numbers, about 10. So yes, we can, yeah, it's fully laminar.
You need to be in the thousands for turbulent flow. Yeah, expected that. Then secondly, at these higher flow rates, on the same line actually, flow rates, are you actually losing signal because of spins leaving the sensitive volume, and have you considered that?
No, we are not losing any signal at the flow rate, because what we actually need to look into is the residence time. So we have looked into that, and the answer is just simply no.
The answer is no, okay.
Yeah.
And then finally, a more application-based question. Do you have any systems in mind that you want to investigate in the future using this reactor? So microfluidic devices in general, they're great scaffold for biological cell cultures and tissue cultures, which we also do in our group. So the ultimate goal of our project is to actually implement a full sidearm hydrogenation. So all the steps, including, you know, the cleavage, the transfer to carbon, and then hopefully just flowing it into a cell culture already in our chip. So just directly feeding it into a cell culture. So that would be the ultimate goal. Yeah, that would be amazing. Yeah. Hopefully. And wow. So I guess with this vision, we thank Sylwia again and transition to our next speaker. Yeah, thank you so much.